In this video we're going to look at the Infnity Commander software to control the Infnity control unit. As you can see, I've created a shortcut on my desktop to the software. Before you start the software, it's very important that you first of all ensure that the USB cable is connected to your laptop but not connected to the Infnity controller. If you do connect the laptop cable, the USB cable, to the Infnity controller before you start the software, sometimes the Infnity controller becomes a mouse and the USB cable will take control of your system. If that happens, don't worry. Disconnect the USB cable from the controller, let the mouse calm down, start the software and then connect again. So, before we start, we've got the USB cable connected to the laptop. We're not connected to the controller, so we can start the software. As you can see, when the software starts up, we have a message showing connect and a title box asking you for connection. Connect the USB cable to the controller. Now you've probably seen that as I've connected, we started to get a little bit of movement on these bars showing that we have connection. But some of the boxes, like this master gain box and the frequency test and phase test enable boxes, are not displaying any results. This is because we haven't read any data from the commander yet. So when we connect, click on connect. You probably heard the control unit beep, and it's now read the data from the control unit into the system. So you can see that it's populated the master gain, frequency test enable's been populated, the data's come back from the controller. So if we have a look around the interface, on the left hand side here we have a number of tab controls for things like advanced detection settings, general detection settings, alarm mapping, networking, viewer controls, general settings. On the right hand side we have tabs for the receivers, general showing alarm counter, monitor showing what's happening with the system, transmitters showing the transmit levels, transmitter currents. So let's look at some of these controls in detail. If we go back to the receiver screen and the general settings screen, general settings screen should be pretty straightforward. The alarm time setting here, that's the number of seconds that the alarm will ring for, and you'll notice that as soon as I make a change, the system beeps. When the system beeps, that confirms that it's received the change and it's stored it in its memory. All system changes are stored in non-volatile memory, so even if the power is removed from the system and the system's repowered, the changes will still take effect and will be remembered. We have an alarm style selector which determines the sound that we get from the system, the different styles of the alarm tone. Read system, that does the same as when we first connected. It will read all the settings from our control unit into the commander software. It's very important that if you're moving from system to system, so you have a store with a number of controllers, then every time you connect to a new system, you must click the read system settings. If you don't, what may happen is that you're looking at a screen and it's showing, oh, the receivers are enabled, frequency test is enabled, but you're actually looking at data that came from a previous system. So I say, when you change from system to system, very important, click the read system setting. Reset alarm, very straightforward. In the general tab here we have an alarm counter. When you click on reset alarm, that resets it to 0. Sounder or speaker volume. As you can hear, that adjusts the sound or the volume level of the speakers. General detection settings. Now this is probably the most important screen you'll work with. The top control, alarm threshold, determines how much alarm signal is needed above background noise before the system thinks that there's a tag and starts to generate an alarm. The higher the number, the larger the tag signals required. The smaller the number, the smaller the tag signal required, and the more chance of false alarms. Typically it's set at 3, but it can be increased up to, as you can see, 20 to reduce false alarms and make the system less sensitive. Pedestal configuration isn't configured at this moment in time, but this would determine how the pedestals are arranged, whether they're transmitting in phase, out of phase, in backfield, reduction mode, different types of system setting. At the moment we can ignore this control. Receive window delay. Following a transmitter pulse, the system transmits a signal at 58 kHz, stops transmitting and waits for a tag signal to come back. If you try and look for the transmitter too quickly, if you try and look for a tag signal too quickly, instead of seeing a tag signal, you'll actually see the back end or the ring down in the transmitter circuit itself. So if you try and look for that tag too quickly, you'll actually see the transmitter rather than the tag. So we have to put a delay in following the transmitter before we start to look for the tag, and this control sets how long that delay is. 60 is actually 600 microseconds, which is typical. Now, if you find that the system is a little bit unstable, we're seeing noise coming in, or we're seeing instability in the tag signal, it may be because this control is set too short. At the moment you can see here we've got very little tag signal and very little noise. If I reduce this control, let's try 30, you do notice now that the tag signal's increased. That's because we're starting to see the back end of the transmitter. If we reduce this too far, the system will start to false alarm. So now we're getting to a point where, there we go, and we get a false alarm. That's because we're actually seeing the end of the transmitter pulse as a tag signal. So we want to keep this delay as short as possible, because obviously as soon as we've stopped transmitting, we're going to start losing any signal in the tag. So we need to start looking for that tag as soon as possible. But as I say, if we look too quickly, we're going to see the back of the transmitter. So typically this should be left on around 60. The default value is 60. TX synchro delay, which is the next control, determines when the transmitter will fire. Normally all systems should be left on 0. This means that the transmitter will fire at the 0 crossing point of the mains frequency. If there are other systems close by and the other systems are not set to 0, they may transmit when we're starting to look for a tag, and as a result of that we'll see the other systems as noise, or worst case scenario, the other systems actually as tag signals. This control allows us to move our detection point and our transmit point away from 0 so that we can synchronize with other systems. This should be used in conjunction with a synchronization meter or other means of testing to ensure that all systems are in synchro. Master gain control, we can put a number in here between 1 and 255 to set the gain on the system. Typically you'll be using gains of around 10 to 20. In very low noise conditions that gain can be increased to increase detection performance. In high noise conditions we reduce the gain to stabilize the system. You'll also notice that there's a gain control for each antenna. This is actually an automatic gain control, and at the moment, as you can see, it's set at maximum. If the system sees noise or thinks it's too sensitive, this gain control will start to fall and the system will automatically adjust the individual gains for each antenna to try and get an optimum signal. Typically you should hope to have this gain control set to a middle position. At the moment, where it's right at the top, it's trying to get more gain than there is available in the system. So we may have to increase this from 2 to, let's say, 8. Because we've only got dummy loads here today, we've not got real antennas connected, we're still getting very little noise. But a combination of this control here, the master gain, and these individual gains can be used to optimize the system performance. Noise filter bandwidth, which is this next control, determines how wide a signal the system will actually look for. Obviously, as you're probably aware, AM systems are looking for signals around 58 kHz. We try and limit the signals coming into the system because obviously anything outside that 58 kHz band we want to eliminate because it could be noise, it could be interference. But tags are never produced absolutely 100% spot on 58 kHz, so we have to allow a certain amount of noise into the system in order to receive tags. At the moment you can see it's set for 4, which means that it's in steps of 100 Hz, so it means that the system will be receiving noise and tag signals within a 400 Hz bandwidth around the 58 kHz. So if we drop that to 2, it's now 200 Hz bandwidth, increasing it to 800 Hz. The larger the bandwidth, the more signal that will come in, but obviously also the more noise that we let into the system. So again, if you have some tags that are way off frequency, having the bandwidth set too low will discriminate against those tags and prevent them from being detected. But by the same token, setting the bandwidth too high will also allow random spurious noise into the system, which could cause false alarms. Typically this should be set to 4, which is a 400 Hz bandwidth. At any point whilst you're working on the system, if you're not happy with the performance and you think you've got into a state that you don't understand, clicking this Restore All Defaults button here will restore everything to its default system settings, which will allow you to start again. So let's have a look at the alarm mapping screen first before we move on to the detailed look at the receivers and transmitters. This screen here allows you to determine what happens for each antenna in the event of an alarm. If we look for alarm mapping antenna 1, we can see that at the moment when an alarm occurs on antenna 1, the LED on antenna 1 will light, the LED on antenna 2 will light, and the LED on antenna 3. We'll also get relays 1 and 2 triggering and the sounder sounding. For each antenna we can determine what happens. So for example, if you want aisle identification, alarm mapping antenna 1, only LEDs on antenna 1 will now illuminate. If we switch off 1 and 3 for antenna 2, only the LEDs on antenna 2 now will illuminate when antenna 2 alarms. Likewise, we can turn off 1 and 2 on antenna 3. So now when antenna 3 alarms, only the LEDs on antenna 3 will illuminate. At the moment, when each antenna alarms, both relays will come on and the sounder will come on. So this is a very useful way of determining exactly what happens in the event of an alarm. So you can have silent alarms by having no sounder and just relays. We can have LEDs only, we can have sounders only, we can have relays only. Any combination for each antenna can be controlled from this screen. So if we take a detailed look at the receiver screen, here you can see the 3 antennas, antenna 1, 2 and 3. And we have an average noise and an instantaneous tag signal for each antenna. Now at the moment, because we're using dummy loads, we only have a very small noise and virtually no antenna signal. If I place a tag in the field, you heard the system alarm and you saw the tag signal shoot up. We do this again for antenna 3. alarm and tag signal shot up. So this is a main screen you'll be working with and looking at to determine the performance of the system. At the top of the screen we can disable any antenna. So we've now turned off the receivers for antenna 1. So if we put a tag here, nothing would happen. Likewise, we can do the same for receiver 2 or antenna 2 and antenna 3. For each antenna we can also enable or disable a number of tests. The first test is the phase test. What this does is when we're detecting a tag, we look for a tag 6 times and we take 6 samples of that tag. Those 6 samples are analysed and all 6 must be greater than the tag threshold, which we set in the general settings, general detection screen. So here we set the tag threshold, so all 6 samples must be greater than that. But then all 6 samples are analysed for the phase of the tag signal. When the DSP processor looks at the tag signal, it can determine a number of features of that signal. One is the phase angle of the signal coming back into the system, and with that phase test enabled, we ensure that all 6 tag samples, the phase of all 6 of the samples is within 90 degrees of each other. Typically from a tag, the phase will always be fairly consistent, whereas phase angles from noise received by the system will be varied and widespread. So by having the phase test enabled, we ensure that the phase coming into the system is always within 90 degrees of each other before it's accepted as a tag. The next control is the frequency test, and we were discussing here about the filter bandwidth. If the frequency is outside that filter bandwidth, the system will reject it and it won't alarm the system. If we disable this frequency test, we no longer look at the frequency of the incoming tag signal, we just accept that it is a signal and it will go straight into alarm. So typically you'd leave this frequency test enabled because it gives you the most stability. The next control here is how we operate the antenna coils within the pedestals or the antennas. In each pedestal or antenna there are 2 coils. These can either be a figure 8 and a square, or in the infnity antennas a top coil and a bottom coil. And this control determines how we deal with the signals coming back from those coils. We can either have the signals in phase or the signals out of phase. If the signals are in phase, then both signals come in and are effectively added together and give you a better tag signal. But noise entering the system will also be added together and you'll have more noise entering the system. If the antennas are set up so that the signals come in out of phase, so effectively you have a positive signal and a negative signal, then the signals can be used to subtract the noise from the 2 coils. So for example, you have noise hitting both the top coil and the bottom coil. By subtracting one from the other, you can eliminate the noise, or eliminate it to a great degree. So this control determines whether the signals are in phase or out of phase. Normally you leave them in phase. If the signals are out of phase and you're trying to subtract one signal from another, the amount of each signal subtracted is controlled by this balance control. And what the balance control does is it determines how much signal comes from each of the coils. So at the moment it's set to the center, which is effectively 50-50. So both coils are equally combining to give us a signal. If we move the control towards the top, then the top coil or the square coil, depending on the antenna, is the predominant signal. And if we move it to the bottom coil or the figure 8 coil, depending on the antenna, is the predominant signal. And by moving this control between the two coils, we can eliminate noise and improve signal performance. As I mentioned earlier, the gain control is automatic, and this will move up and down depending on the environmental noise that the system sees and how the system tries to adapt to that noise. We can change the control, but if we change it now, over a period of time, the system will automatically adjust that back to what it feels is the optimum situation. So if we look at the general screen, we now have an alarm counter showing 3 alarms. If I put another alarm into the system, that goes back to up to 4. If we go to the general settings, we can reset this counter by clicking on the reset alarm button. The monitor screen is incredibly useful. This should be used in conjunction with the main controls to see what's happening with the system. At the moment on the monitor screen you can see we've had alarms on antenna 2, antenna 3 and antenna 1. The last alarm we had was at 1412 on antenna 2. The tag level was 121, the noise level was 10. Prior to that we had an alarm 466 at the tag level, an alarm level of 10. Now at the moment all we're seeing here is alarm levels. If I disconnect one of the antennas, there we are, you can see that because the antenna was disconnected, let me show you that on the screen. There we are, we get a lot of noise in, there's no antenna connected. Go back to the monitor screen. You can see that we didn't get any alarms because we had a phase spread fail, and the phase was 103, 107, 128, 116 degrees. You remember we talked about phase being no more than 90 degrees. And also the frequency spread failed. Frequency deviation was 55 and the spread was 7. It should have been 4. If you remember our general detection settings, filter bandwidth was 4. We got a spread of 7, so the noise was rejected. So this is very, very useful for highlighting what's happening with the system and give you an indication as to if it's not alarming, why it's not alarming, because we've obviously got phase spread alarms or phase spread rejection. If it is alarming, then why is it alarming and what are we seeing? And at the top here we can clear the buffer and we can also read the event log. Okay, so we've got the alarms in there, time it was powered up, etc. The last screen we'll look at today is the transmitter screen. Now this shows the transmitter voltage, the large bars, and the transmitter current for each of the coils in each antenna. So we've got 3 antennas, antenna 1, 2 and 3. We've got a figure 8 and a square coil. We say figure 8, depending on the antenna it could be 2 square coils, top and bottom. And we're currently showing the amps in the figures in the square and the amps in the figure 8. On the right hand side of the screen we have the transmitter power control, and by sliding this control up and down we change the transmitter voltage and the transmitter current. We turn it back up again. Now the transmitter voltage and the transmitter current is important because the transmitter is the device that wakes up the tag. If you don't have enough transmitter signal, then you won't get any energy into the tag and you won't get a response from the tag and the system won't alarm. We can see here the transmitter current. It's important to view the transmitter current because when we are tuning the antennas, which we'll do in a separate video, as you make the antenna jumper changes, the current on the antenna will go up and down. And what we're trying to do when we tune is to maximize the current in each coil. So when we're tuning, we'll be viewing this screen and watching the current for each coil rise and fall. So that gives you an overview of the controls on the Commander software for the Infnity controller. I hope you found it interesting and useful. Please watch some of our other videos showing the web interface, tuning, IP setups, which are all available on our YouTube channel. Thank you.